All right. Oh, you guys cannot see a single thing because I haven't switched the channel. There we go. Okay. All right. So I'm going to write a very quick sample program and explain, one little thing that will be very helpful for this particular homework assignment. Okay. I am going to start with a C program that does not seem to be very complex, but it has everything to do with what you guys actually need to do. So uint8 underscore t12 does not take any arguments, and I'm going to return 5 plus 7. Okay? Then I'm going to write the other two subroutines. 5 just returns a constant of 5. And then you can probably guess what 7 is going to do. There we go. Okay. So now the question is, how do we write this program in assembly? I believe so, but it's good to check. Yep. So let me double check. I am recording. The voice is good. It's streaming. So even if this computer were to explode right now, we know the content is already at YouTube. Isn't that great? Doesn't that give you an exceeding level of comfort right there? Yep. And the AC gives you the extra level of comfort right now. Okay. So we're going to look at this program because, I wonder how this program relates to the program that you guys have to write. So now we will look at the assembly version of this program, okay, using a different window. And when this is all done, I would even use the tool that I talked about today, the trace analyzer thing, so we can actually kind of look at how things are happening on the stack, with the stack pointer and all the registers and crazy stuff like that. Okay, so we'll go ahead and write 12, TWELVE, and okay, let's write the simple ones first. Okay, let's write 5 first. So 5 is LDI A5. And then we have the return sequence of instructions, which already know as LD, BD, increment D, and then JMP B, like that, right? Okay, so we know this part already. And then here's 7, LDIA with 7, and then the same 3 opcode to perform the return operation. Nothing too exciting right now, okay? So when we get to 12, we will try to do the same thing as what the C code is doing, which means we have to call 5 first. Well, do we know how to call a subroutine? I hope so, because we have been talking about the same thing, for the past few classes. So, okay, so it's not too bad. LDI, yeah, we can use register A, B, or C. I'm just going to use register A here. And I'm going to use the new approach, which is .6 plus, which is basically 6 bytes from the LDI, from the address of the LDI instruction itself. Decrement D, make space on the stack. STDA to push the return address on the stack. So now we are ready to jump. So we have a JMPI to, in this case, 5, which is the subroutine that we are calling. Is that okay? So when 5 returns, okay, yes. What is what? Line 14. It loads A with the address of the instruction right after the JMPI instruction. Dot is the address of the LDI instruction. This is postfix notation, so .6 plus is what we normally spell out as dot plus 6, basically. Okay. All right. So now now that the subroutine has returned, the first question is, do we have any arguments to deallocate from the stack? Well, the question is, did 5 need any arguments? No. So we don't have to adjust the stack in any way because there are no arguments. Okay. What is in register A at this point? On line 18. The return value of 5, which literally is just a constant of 5. So I kept changing the temperature of the thermostat, and it keeps dropping the temperature, even though it's in cooling mode, and I set the thermostat to 86 degrees, and it keeps dropping the temperature from 66 to 64 now. I can turn it off. I'll turn it off because in heating mode it might overheat as well. I think the thermostat is just has a has a has a stack exploit running right there. Okay, somebody hacked it, right? Okay, so at this point, we have register A as the result of function 5. How do we call function 7? Kind of the same thing, right? Copy, paste, change the 5 to a 7. But this is the problem, because if I do it this way, I am immediately clobbering A, which means I'm losing the return value of 5. Okay, so somebody may say, oh, that's an easy one to fix. We just have to use a different register. Okay, change this to B, change this to B, and everything is good. Nope, that is not the case. Because guess what the subroutine 7 is going to do? What is 7 going to use? What is the subroutine? It's going to return the value 7 in register A. So now the return value of 5 is gone again. Okay, so now the question is, how do we solve this problem? There is no way you can actually prevent a subroutine from clobbering any of the registers. Okay, register A, register B, and register C, they can all be clobbered or overwritten by a subroutine that you're calling. If you have a register that has a special meaning to you and you don't want to lose its value, the only thing you can do is to save it on the stack. Okay? So how do you save something on the stack? You decrement the stack pointer first, and then you do a store into what D is pointing to. The typical way of pushing something. Decrement the stack pointer and then store to what the stack pointer is pointing to. Are we good so far? Okay. So now, when 7 returns, what are we going to do? Well, we got two things now. Register A has the return value of 7. But the return value of 5 is on the stack. Right? So what we need to do now is to say, okay, go ahead and retrieve from the stack the return value of 5. So I'm putting the return value of 5 into register B. But now that location has no use to me. I'm going to increment the stack pointer to pop the item, okay, to remove the item on the stack because it has no use to me anymore. But now I can use the add instruction to add B to A, because register B has the return value of 5. Register A still has the return value of 7 because we just got back from 7. So now register A has the sum of the return values of both of those function calls. Is that okay? Now we can do the usual return sequence, which is the last 3 instructions of that. Okay. Copy and paste. And that's it. That's how we implement 12, even though it has 2 function calls. This is how we save the return value of one function call on the stack, do the second function call, pop the return value of the first call, and then combine that with the return value of the second call. I hope you guys are seeing some resemblance between this and the code that you have to write. I mean, there are certain aspects of your code that I'm not addressing, like arguments, okay? And I did mention a few times, oh, we do not have any arguments to deallocate. But if you do have arguments to deallocate, you have to remember to do that. Is that okay? The caller is responsible to deallocate arguments. Yes?
So the return address, the subroutine gets rid of that off the stack, but then the caller gets rid of the parameter.
That is correct. Yep, so all of that is actually written in a particular document. So now we can now go to main, okay, just to finish this program so it can run. If you want to use the trace analyzer, you have to precede everything with a no-op instruction. It is a bug of Logisim that requires this no-op instruction, but it seems to fix the problem. So just remember to put a no-op instruction as the very first thing to do in your entire program, and that's all you need to do. So in this case, we are just going to call the subroutine. Okay, so we'll say LDI. Oh, yeah, LDIA with .6 plus. And I'm not storing it to any place, okay? So from the trace, you will find out, how I know the program does work. And then we have a decrement D, STDA, JMPI to 12 in this case. When it comes back, I got nothing to do. I'm just going to halt. Is that okay? So do we have any questions at this point about the implementation of this code? Oh, that's supposed to be a dot. Thank you. There we go. So are we good? Yep.
With the dot 6 plus, does that mean it picks up on the 6th byte, or does it mean that it picks up on this after the 6th byte?
It means it's using the address of the LDI instruction itself, and then add 6 to that value, and whatever that value is stored in register A.
So it would be,
It'll be the halt. It'll be the address of the halt instruction.
this halt is the 6th byte.
Yes.
Okay.
So if you count bytes, then LDI itself would account for byte 0, byte 1. Decrement is byte 2. Store is byte 3. And then JMPI would be byte 4 and byte 5. So byte 6 is the halt instruction, which is exactly where we want the subroutine to return to. Huh? It's like having a label name, except you don't run into the risk of copy and pasting and using the wrong label as a result. This is always copy and pastable, as long as you change the label of the subroutine that you're calling. Yep.
Why is the JMPI 2 bytes?
Huh?
Why is it 2 bytes?
Every instruction that has an I takes 2 bytes because you need 1 byte for the immediate value. So this goes back to how instructions execute, how we use the program counter to point to the immediate value, which is 1 byte after the opcode itself.
Can you scroll down a little bit?
Yep. So with 12, this is the call to 5. This is the call to 7. The code in between is push A. I'm saving register A on the stack. So once I save register A on the stack, I can reuse register A for whatever I want, right? Because the value is already on the stack. When 7 returns, then I pop A from the stack into register B. Now register B has the return value of 5, and register A still has the return value of 7. Adding those two is exactly what I need to do in the C code. Are we doing okay so far with this? Okay, I will save this code and make it available to you guys. So when you get it, you want to kind of annotate everything with your own words, okay? And that's why I'm not typing any comments here. I'm leaving it to you guys to comment it, because it really helps when you write it in your own way to explain it. So are we good so far? All right. So now we're gonna take this code, Control A, switch back to the browser, go back to the assembler, which is taking a nap right now. Go to the source tab. The source tab has a lot of stuff because that's the Tower of Hanoi thing, and I think some of you may want that too. So I'm going to try to save that first. So let me save that first. Okay, copy that, and paste it into another window. There we go. And then now we can clear. Oops. And then we have to copy and paste the other program in. Copy and paste. Double check, make sure there's no error. Okay, it's all good. And then go to RAM file, download as CSV. And I'll just call this 12, TWELVE. Then go back to the command line. Did I lose the big one? Nope, there you go. Okay. Go back to here and repeat the command that I have like way back. Nope, that's not it. All right, so to repeat this command here and make some slight adjustment to it. All right. So the only thing I have to change is the name of the CSV, which is now 12, TWELVE. Everything else can stay the same. Press the Enter key. So the program is now done. But I have a log as a result. So now I need to go back into the trace analyzer, which is this guy here. Okay, so if you do not remember how to use the trace analyzer, go to sheet 1, go to the first cell, but don't double click it, don't make a blinky cursor. Go to File, go to Import, go to Upload, and then specify the file that you upload, and that's going to be my log.tsv file. And here's the important part. The important part is replace the current sheet. Do not replace the spreadsheet, because if you specify replace spreadsheet, then all the good stuff is gone too. Okay, so only replace sheet, not replace spreadsheet. The second one, you want to pick tab, because it's a tab separated file, not a comma separated file. And the last one, you have to say no, because otherwise it will convert numbers when it is convenient, and then it's not going to work if you specify yes. So now that we have all of these specified, click Import Data. And it's only going to overwrite some parts of Sheet 1, but Sheet 2 will still reflect what the program is doing, like this. And it just takes time to refresh. So some of the leftover stuff from last time was still here. Okay, now it's all done. So let's check out this program and see what it's doing. And what we'll be doing is we are paying particular attention to what we're doing on the stack. Okay, so we can see that right here we are changing the stack pointer. We are basically decrementing the stack pointer by 1. Which instruction is doing this? The instruction at location 05 is the one that is decrementing the stack pointer. Okay? Well, are you guys buying it? You guys are going, yeah, we'll buy it. I should have been a used car salesman. I would have been rich as a used car salesman. No, you're not going to buy it. You're going to double check it, right? You're going to say, that Toyota is not worth $30,000. Because you're going to go check the Blue Book. So the way you check is to go to the assembler and go to the source debug tab, and you go to location 5 and you ask, is this instruction supposed to decrease the stack pointer by 1? And the answer is yes, it is. Okay, so this is how you can debug your program, is to look at both the trace analyzer and also this particular tab of the assembler. Okay. So what is of particular interest to us in the trace analyzer is where do we specify the return value of 5? Where is that going to be? Well, you have to look at register change when A changes to 0, 5. That's probably where we return the value of 5 inside the subroutine 5. Okay? So we scroll a little bit and then we find that right about here. Okay? So this is where we return the value of 5 from the subroutine 5. Okay? This is where we got the return address. Okay, remember we did the LD B in parentheses D. This is where we got the return address. Now, how do we know 1A is the proper return address? Once again, you go back to the assembler. You go to address 1A, and then you ask yourself, does this look like a good location to return to when 5 is done? Well, this is the call to 5. Where else should the subroutine return to? Of course, it's going to be here. Okay? All right. So going back to the trace again, which is here. So now we pay attention to what we're doing on the stack. The stack pointer got changed from FE back to FF. This is done by the subroutine. This is done by 5 because once we retrieve the return address of 5, we have no use of the return address on the stack, and then we increment the stack pointer to deallocate that byte from the stack. Okay? This is how what you're supposed to do when you look at the trace analyzer, is really to correlate what the program is doing with the code or the source code of the program. And then what do we do? After this, we continue execution, and you can see how the instruction pointer is changing a little bit. Let's see, this is decrementing it, and this is where we get back to the return address. Do you see how these two are not right next to each other? Because any opcode that is right next to each other can only be off by 1 or 2 bytes. The longest instruction that we have uses 2 bytes. When you look at 0E and 1A, they are off by way more than 2 bytes. So this tells us that this is the result of a jump instruction, which is actually the JMP-B at the end of the return of the sequence of instructions that performs the return. So now we are back to 12, okay, the subroutine 12, and look at what we are doing here with the stack. The stack pointer got decremented again because it went from FF to FE, and then we store something over there. The question is, what are we storing? This column tells us that we are storing F05 into the location FE. That is the return value from calling 5. So we stash it on the stack, okay? Then we perform the call to 12, which is done by all this stuff here. This is the return address of 12. And then we continue execution at 12, which is probably this instruction here. 7, excuse me. We continue, we're calling 7 from 12, so we continue execution in 7. And then inside 7, we specify the return value of 7 right here. And then we return back to the caller. And the return back to the caller is here. So we are now back to 12. So location 22 should be in 12 right after 7 returns. Now, you can say that, but TAC, you can say anything you want because nobody can actually keep track of all this stuff. But yes, you can, okay? If you have the same tools that I have, you can open. Now, if I were you and not using the projector, I would open 2 windows. One window for the assembler and one window for the trace analyzer. So this way you don't have to switch back and forth, okay? But the real estate of the projector is limited, so I kind of have to juggle with all this stuff here. So now we get to location 22 and figure out, okay, what is at location 22? Location 22 is right after 7 returns. Is that okay? So right at this moment, what is the return? Where is the return value of 7? It's in. Huh? This is right after 7 returns. Where is the return value of 7? Register A, very good. Good job. So register A has the return value of 7. Where is the return value of 5? No, not register B. It's on the stack. Okay, it is still on the stack, but not in register B. So now we switch back to the trace analyzer again. So when we look at this, okay, see this part here? This is a read operation, a memory read operation. It's reading location FE and it got the value of 0.5. So this is how we retrieve the return value of 5 from the stack into register B. So you can see how we are reading location FE, get its value, which is 0.5, and then use that to update register B. So now we got both return values, right? The return value of 7 is in A, the return value of 5 is in B, but there's one little bookkeeping thing we have to do. We have to remember to increment the stack pointer, because that return value of 5 is no longer useful on the stack. I just put it back into register B. So we have to increment the stack pointer to deallocate that item from the stack. Then we can add those two, and then we end up with C, which is 12, in register A, which is the return value of 12. And then the rest of the program is just returning from 12 back to main, and then the halt instruction. Question? Oh, okay, you're just, okay. All right, so do we have any questions about this, the analysis of this trace? But are you guys starting to see two things, okay? One is the relevance of this sample program to what you guys need to do. And then the second thing is how this tool can be useful for debugging programs. But in order to use this tool, you need to have an understanding of what the program is supposed to do. And then this tool can show you whether your program is doing what you think it should be doing or not. When what you expect the program to do and what the trace is showing you differ, when they are not the same anymore, then you have to stop and you have to think, why is it different? Okay? But at least it gives you a tool to visualize what is happening with the stack pointer, the registers, and the content on the stack. And you can basically, you can print this out too. I mean, you can just select a small portion and then print that portion if you want to. You can save it onto a local spreadsheet and analyze it, using some other tools or whatnot. So are we good so far? Okay, so if I were one of you, I would have asked another question. I would have asked this question. I would have said, where is the other one? Where's the C code? Right here. I would have asked this question. I would have asked, but this is not recursive. My program, the program I'm supposed to write, is recursive. How is this going to help me? What do you think is the answer? Why would it matter? How you call a subroutine is the same. If you have Fibonacci calling Fibonacci, it is no different from 12 calling 5 or 12 calling 7, because you go through exactly the same motion. The caller push all the arguments, push the return address, jump into the subroutine. The subroutine will utilize the arguments if there's any, pop the return address, get back to the caller. Then the caller has to deallocate the arguments on the stack. That agreement doesn't change. Whether you are calling different subroutines or whether you have a subroutine calling itself, the convention of calling a subroutine and returning from a subroutine stays exactly the same. That is why it makes no difference whatsoever whether it is 12 calling 5 or whether it's Fibonacci calling Fibonacci itself. Okay, if you're thinking about, oh, but Fibonacci calling Fibonacci itself looks like a loop, then you are overthinking. Is that okay? All right. So I'm going to stop the recorder unless you guys have any questions. Why is it so cold?
Yeah.
That's actually a line from one of the songs that I really like. Why is it so cold? Okay, so I'm gonna stop the recorder.